Okay, so it's a pleasure to finish this one day of very interesting talk with the talk of Laure Zanna. Laure is a professor at New York University, both in applied math and application to climatology and AI. So Laure, you have the stairs, so it's up to you.
Great, thank you very much. And thank you very much for staying until the end of the day. I'm sorry I couldn't join you in person. I was very excited about joining the Collège de France, which would have been the first time. But again, I appreciate the opportunity to tell you a little bit about the work we've been doing on using AI to, I would say improve climate models, or at least rethink a little bit the way data and AI together can help us move forward in understanding how different components of the climate system works. So I want to try to kind of, start the talk in a way that kind of present the grand challenges. And I think it's always important to kind of, think about why we use climate model for. And in general, any simulation has a lot that it can offer. One of them is accurate predictions, right? And I'm sure you heard a lot about this, throughout the day. But quite often for us, it's kind of trying to understand the multi-scale, multi-physics aspect of the climate system. I come from the physical oceanography side, and I'll tell you a little bit about the type of scale interaction that we try to understand. And it's really understanding, how the ocean mixes, heat, carbon, oxygen, and so on and so forth. And really, it's really a beautiful type of scale interaction in a stratified rotating fluid that has been a pretty big challenge for a long time. So the way we see using AI is really trying to be smarter at the end of the day. There's something that we can learn about the multi-scale interaction that we've been doing traditionally with numerical simulations, traditional numerical simulation and basic physics and data that can help us move faster and understand those processes faster. The second aspect is computational, right? And so, we do end up with new architectures and new hardware, GPUs for the most part, that can help us run simulations faster. So again, if you can do things faster, you can explore a larger space overall and being able to actually advance scientific discovery. The last one, I think this is very important in terms of grand challenge, right? So we want to be smarter. We want to understand scale interaction. We want to have computation that is easier of reach, right? So we want them to be fast. But, I'm a physicist by training. And so I want something that will be robust. So if I learn something from data with advances in architecture, there has to, in the machine learning world, it has to generalize. And for us, that means that it has to be robust to changes. And so, if I have a simulation of interaction between the ocean and atmosphere, it should be true for the present day climate, or if I wanted to look at the last glacial maximum, the physics should be the same to some extent. The forcing is different. So those challenges are true both in the era of AI, but they were true in the past and they will continue to be true. We really want to understand how scale interact with one another in the complex, climate system. We want to have simulations that are faster, and that's where, potentially AI can help, but other traditional method can help as well. And everything we do has to be robust. It has to generalize. And so I want to, kind of focus on those three challenges as I go through this talk, because that should be the holy grail, not just accurate prediction in a way. Okay, so I'm always very grateful to be invited, to many things. But at the end of the day, everything I'm going to say is definitely me saying it. But the work is teamwork, and it's a part of a large project that is supported by Schmidt Sciences called M2 for multi-scale machine learning and coupled system modeling. And so our goal is trying to reimagine or kind of reinvent the way we do climate modeling with data and AI for scientific discovery. And so we are basically about 40 people by now. We are a range of domain scientists, I'm a physical oceanographer, for example. We have atmospheric dynamicists, sea ice experts. We have machine learning experts. And so, people who really kind of develop new algorithms, in machine learning. And we have climate modelers. So people who actually build climate models. And so it's really an interaction between all of us. And everything I'm presenting, is very much kind of collaborative work. Okay, so let's start with grand challenge number one, which is understanding multi-scale, multi-physics interaction. So just to give you a little bit of context, and it's at the end of the day, so I'm going to try to not be too technical and hopefully kind of give you an idea of the type of challenges we're facing. So here is a paleo record that shows temperature, so changes in temperature as a function of time. So present days over here. And then as we go to the left, we're basically going backwards in time. And so we're looking at the paleo evolution over 60 million years before present. And so again, the record is collected from different paleo proxies, but it's just to give you a feeling a little bit of the very large type of fluctuation that we see in the climate record. And so, this is us here today, right? So we have temperature going up. In the previous 100 years or so, things were relatively stable. The mid-Holocene was also roughly similar to what we have now before the Industrial Revolution. But we had periods that were a lot colder. We had large swings during the last glacial maximums. We had periods that were a lot warmer than what we're experiencing today, where you had palm trees all the way up to the Arctic. So the climate system really is this kind of very complicated interplay between the ocean, atmosphere, ice sheets, and so on that, kind of oscillate on many timescales. So when you want to, understand the climate, you have a lot to understand, right? So, and those kind of swings in temperatures are coming from many different processes, some internal to the climate system and some external as well. So if we zoom in, right, so I give you a picture of the global mean temperature changes, but then if we look at the physics of the system itself, then the granularity of it is actually pretty exciting. So here I'm showing two movies from the same simulation. So it's a simulation run at 1/48th of a degree horizontal resolution. So then it's the size of the grid box size. So this is surface velocity, and this was eye thickness. So I just play it again. So here we basically are emulating about a little over 1 year of the ocean plus ice interaction in this simulation. And it's just to give you a visual, a little bit of what I'm talking about here. So this is the Gulf Stream here, so large scale current detaching from the US East Coast. And you can see a lot of, swirls and what we call eddies of many different scales. And so those are derived from the instability of the large scale currents. So they kind of extract energy and momentum from the mean states and interact with one another. And then for the sea ice, what you're seeing here, obviously, is some of the sea ice actually cracking and merging together, but also being transported by the underlying flow. And all of it is being forced by atmospheric variability. So a huge amount of interaction over a wide range of scale across different type of fluid. One that is relatively viscous in some ways, right? And when we think about ice, it's a non-Newtonian flow, while you have a Newtonian flow for the ocean, but again, highly turbulent, very high Reynolds number. And all those interactions together actually do influence the mean temperature of the planet. So you have a lot of scale that interact with one another. Just to kind of continue giving you a range, a little bit of that scale interaction, because I always think it's important to kind of think about the real challenge that we have. So when we think about, the large scale currents, so I told you about the Gulf Stream kind of detaching from the US East Coast, it's usually driven by large scale wind. And so you're going to have scales that are about 1,000 kilometers. And, it changes on time scales of years to decade. And then you have, some of those mesoscale turbulence that you could see in the movie. They have about 10 to 100 years kilometers. And again, they derive their instability from the large scale currents. But then you have other scales that have about 1 to 10 kilometer that again, are both an interaction of instabilities from the larger scale, but also interact with the wind stress and so on, all the way down to dissipation. So we're really thinking about a 10 to the 8 kind of difference in scale that you need to capture. And if you want to understand present day climate, then you would have at least, 10 to the 10 seconds that you want to understand just for a few decades. So you can already imagine the scope of the simulation you would need to have if you wanted to understand how mixing influences sub-mesoscale that influence mesoscale that influence the basin scale, and then at the end of the day, understand how the ocean takes up heat and carbon and moves it around, right? So it's a massive challenge to actually resolve all those scales, both spatially and temporally. So what do we do, right? So, I mean, to some extent, many of my colleagues in physics tells me that my problem is not that difficult because I have equations of motion, right? So I can write the Navier-Stokes equation, which are, Newton's law, basically, and conservation of heat and salt and so on and so forth. But again, right, hopefully you get the gist by now. Lots of interaction, lots of scale that we have to basically solve. And again, even mathematically, we can't resolve those equations by hand, right? So what we do is we usually discretize them. There are many methods out there, right? Finite volume, finite difference, spectral methods. Though I should mention spectral methods for the oceans are not a favorite since we have continents everywhere. But again, the holy grail of climate modeling has been to take those equations, discretize them. But of course, we're gonna be limited by the grid box size, right? So the number of grid box that I have will, basically limit the computation. So more grid boxes, more computationally expensive it is. So just to give you again a number, so you get an idea. So if I were to assume that every box is about 1 meter, so the size of one grid box is 1 meter cubed, so 1 meter by 1 meter by 1 meter. And let's assume that every box in the ocean, evolve independently from one another. You'll end up with 10 to the 28 equation just solving for the ocean dynamics, right? Without thinking about the other components. So it's completely an intractable problem if I want to, understand how mixing will influence the large scale ocean circulation. So today climate models look something like this. We mostly resolve this part of the spectrum. So, we basically resolve the large scale circulation. We partially resolve those mesoscale eddies, which have, about 10 to 100 kilometers in scale. The current generation of climate models has a resolution of about 25 kilometers horizontally, roughly. And that means that everything that is in gray over here is either completely unresolved or only partially resolved, like the mesoscale. So you have a large chunk of turbulence that is not resolved by the current generation of climate simulation. And so in general, what we do is we come up with, for those of you who are applied mathematicians in the room, we come up with a closure. And if you're more familiar with the term, parametrization. So we try to come up with an empirical fit for how those scale interact with the large scale. And usually it's not like we had a lot of data to do this kind of things. So it's mostly kind of, thinking about how the physics works and coming up with mathematical operator that will represent how mixing influence the large scale temperature, for example. So climate models then are run this way, right? So you basically take the equation, you discretize them, you solve them, on this grid, and everything that is happening below the grid. So, for example, as I said, mixing all mixing processes in the ocean and cloud radiation, air-sea interaction in the atmosphere, all of that is being parameterized. So your equation looks like this. You have a tendency, so the rate of change of, say, temperature, momentum is going to be equal to something that is being resolved. So whatever transport that you have that is larger than the grid box size that you have, plus some subgrid scale that will need to be parameterized. And so you can understand, right? We have a lot of assumption that goes into this kind of yellow box of all the turbulence in the ocean. And so that will have an impact in terms of the accuracy and the faithfulness of the simulations that we have. So in a cartoonish way, how climate simulation is being run, well, you start with an ocean state, then you have some resolved transport. So that's going to be our partial differential equation, right? So where the physics lie. Then we're going to add a term that comes from the parameterization. So all the unresolved scale. Usually there is some forcing. So for the ocean, it's going to be, say, wind forcing, heat fluxes at the surface. And then it's going to give me the ocean state at the next time step. So again, I'm kind of abstracting it. Many of you are familiar with, numerical integration, but just in a cartoonish way, it's going to tell you, how simulation works. And so, of course, this part here in the middle, right? So the parameterization is a big challenge for us. And I just want to show you, again, I think climate models, by the way, are wonderful, right? So whether climate model, whether it's for the atmosphere or the ocean, they're doing an amazing job. But again, there's a lot that we don't capture. So if we take, any climate simulation today, in all honesty, you will see roughly the same pattern. So you run it for about 40 years, over the historical period, and then you compare it with a 40-year mean coming from observations. And here I'm showing the temperature difference between a 40 years average of a simulation and a 40-year average of the observations. So where it's red, that means that the model is warmer than the observations. Where it's blue, that means that the model is colder than the observations. And so you can see the North Atlantic, for example, large error in the simulation. The Kuroshio in the Pacific, same thing. The Southern Ocean, you also see this dipole of warm cold. And in general, a lot of those errors come from missing turbulence. So here the Gulf Stream detaches and usually transport warm water to high latitude. And so this bias, this error that we see in the model is because usually there's not enough northward heat transport. So the Gulf Stream accumulates a little bit too much heat and doesn't transport it to the North Atlantic. And so that's something that's been around for actually several decades that climate models struggle to actually do right because there's not enough turbulence that feeds the Gulf Stream to make a lot of the transport faster and more efficient than it's supposed to be. And that comes by the fact that we don't have accurate representation of turbulence in the model. So traditionally, as I said, it's what I call physics-based. So you come up with a mathematical operator that will represent the effect of turbulence onto the large-scale flow. The other approach, and I don't know if Michael Brenner talked about this, but there is kind of the approach of replacing all the physics with something that is learned directly from AI. So you replace the entire subgrid physics with neural networks. And we've done both of it, by the way. We've done the physics-based and we've done the neural network aspect of it. And again, both can be useful, both have their biases. But one thing that we thought, could be fruitful, or at least potentially fruitful, is to interrogate the data in the way that we can interpret it, right? And again, neural networks are amazing. They can capture a lot of patterns, but they're pretty hard to interpret in terms of understanding what we can capture out of it. So again, we still use them, but I'll just show you an additional kind of aspect that we were trying to extract here. So what we've done is, rather than come up with a mathematical operator ourselves, or again, a big neural network, we decided to use sparse regressions, basically sparse Bayesian regression, and trying to learn the operator directly from the data. So we took simulation that resolves the turbulence or part of the turbulence, and we asked an algorithm, so either sparse regression or any symbolic regression tools that you want, to extract a mathematical operator that will describe the effect of the turbulence on the large-scale flow. So I'm not going to go into the detail. I know it's the end of the day, and on Zoom it never works out too well. But this is the operator that we were able to extract directly from data that tells us basically how the mesoscale turbulence, so again, 10 to 100 kilometers, that usually we inject momentum and energy into the large-scale flow, can be represented in terms of a mathematical operator that is being extracted directly from data. So what we were pleased with, and so we give the algorithm a library of function, and then it basically extracts a set of basis function that we give it, and kind of mold them together. And so what we were happy about is we could extract a tensor that one is symmetric, which is what we expect because we're redistributing momentum and energy into the flow rather than creating it by itself. And so we have to respect some symmetry of the internal fluid dynamics. Also dependent on key quantity that we know are important for turbulence. So again, if you're familiar, vorticity, shear, and stretching, which are some of the key ingredients, and really kind of, basically help us to understand how the different scales interact with one another. So here we extract a mathematical operator that serves as a closure into the simulation directly. But again, we were able to actually understand, might be a big word, but easier to interpret and to do some, for people like me, geophysical fluid dynamics on top of the tensor. So the first good news is after we capture this kind of mathematical operator, we now are able to plug it back into the model and rerun the simulation and see what the response of this new closure looks like. So just zooming in on the North Atlantic. So this was, again, the sea surface temperature error of the original simulation, right? Too warm Gulf Stream, too cold North Atlantic because there's not enough heat transport. Now, if we add this new closure for the mesoscale turbulence, that's the response of the model. So to be clear, this is not the error, it's just the way the model responds after we add it. So if you want to look at the error, you have to take this and sum it with this. And the bottom line is you would get a reduction of about 50% of error. And so what happens here is that our new closure re-injected energy and momentum into into the large scale transport. So that accelerated the Gulf Stream. And that means that the earlier accumulation of warmth here and not enough heat transport in the North Atlantic has been alleviated. So now the Gulf Stream is actually faster. There's more transport of heat because we have a better representation of the turbulence effect on the large scale flow. And again, to be clear, this is not added after the fact, right? It's a full nonlinear simulation. So it interacts in the way it wants. So the good news is we were able to actually capture energy and momentum in terms of its conservative property. It's interpretable because, again, if you do fluid dynamics, then or at least applied math, then there is a lot that you can extract from this operator. I didn't talk about that, but it's resolution and flow aware. So why is it flow aware? Because it depends on actually how we resolve the velocity gradients. And so that means if you have a model that has coarser or finer resolution, the amount of turbulence that you input will actually change based on the velocity gradients. And it's resolution aware because this kappa over here that is also extracted by the algorithm scales with the grid box size. So again, if you change the resolution of your simulation, the amount of turbulence that you put in relatively will change. I say in principle, it's easy to implement. And I say in principle because I'll come back in a second, but basically the bottom line, it's an equation. So we know how to discretize things like this in a proper way. And it reduces biases or errors in the North Atlantic by about 50%. Now, the challenge is it's like playing a game of whack-a-mole. We fixed the North Atlantic, but we actually did not improve the Southern Ocean. So we kind of know why to some extent is because we're only capturing one aspect of the turbulent effect in this closure. There's another aspect that is related to buoyancy rather than momentum that we haven't captured. So, we're working on this. So it's not because you're solving one problem that you've solved everything. And the second thing is, and I think it might be kind of interesting for some of you in the audience that do works on kind of, numerical methods, is that at the end of the day, we still started with, a simulation that was discretized on a certain grid for which people have made, certain assumptions about, the additional subgrid closures that are there, how you discretize the equation on the grid, and this interaction between the numerics and, the new parameterization is a very subtle aspect. And this is not one that is easy for us to understand, yes, because again, there is a lot of interaction between the existing numerics and whatever we add to the model. And that's true for any closure that you would put in. And so that continues to be an interesting challenge to kind of think about as we move forward. So, we could say, well, that's it. We solved everything. We have better coarse resolution models of what we call those hybrid simulation. Part of it is literally the physics-based transport that is well resolved. Another aspect of the subgrid that is directly learned from data. So in this case, I showed you something that was, based on an equation extracted from data. But as I say, we also do it with neural networks of different flavors. But there's still quite a few challenges in those hybrid simulations overall. One, of course, we're still running at relatively coarse resolution, right? So there's a lot of physics that is missing there. And I'll come back to it in a second. So one is numerical stability, right? So that it's still kind of hard to couple those data-driven plus physics model and keep them stable. And it's true of any model for the main part. I didn't talk about uncertainty quantification, right? And the type of data that you could use. So been doing a lot of other things on that respect and, just kind of to flag a few and hopefully might kind of inspire some of you. So we're still learning, representation, and any representation is imperfect by definition because it's only an approximation of what the turbulence does on the large scale flow. So to try to capture, the uncertainty with it, we've been trying to think about using stochastic parameterization and stochastic closures to learn an uncertainty associated with the representation that we have, right? So rather than learning a deterministic model of the turbulence, we try to learn a stochastic one. And so there are many ways to do it. And so again, we basically learn distribution either by assuming the shape of the distribution and we learn the moments, or we let generative AI just basically kind of come up with a distribution based on the data that we have without assuming it. And so that's one way to kind of introduce uncertainty quantification in the representation of turbulence scales that we have. Another aspect, and this one I actually feel more strongly about, and it's still early days. There are a lot of people working on this, right? How to embed symmetries and invariants in building closures. I think we're not, I would say that I think it's an important aspect, but we're not quite there yet. And so here is a few things that we've been working on, right? So either by normalizing the input and output of the closure that we're trying to learn. And so what I mean by that is using, for those of you who are familiar, Buckingham Pi theorem, right? So you find the right kind of dimensional scaling. So we reshape the conditional distribution that we're trying to learn. So then they become invariant to different changes in forcing, right? Because if I learn physics, then physics is true again if I am in a regime for which the wind is weak versus the wind is strong, right? I would not write a different Navier-Stokes. The equations will be the same, but you'll get different properties that will be emerging. And again, kind of, thinking about ways to learn in a way that is coordinate invariance and, kind of embedding rotations and symmetry. So there are a lot of ways to do those things. And again, I still think that there's a lot to explore for which we didn't find quite yet, something that is generalizable enough. And we hear a lot that sometimes everything is in the data, but we don't have infinite data, right? So trying to make sure that whatever we learn is robust and can generalize to different climates. So it's something we've been working on. Okay, so now I want to kind of switch gear a little bit and kind of ask a big question, which is, okay, we have a model, right? We resolve part of it. The subgrid is represented by a data, driven model, but there's still a lot of physics that are missing, right? And a lot of feedbacks, and we're still limited in some respect. So is there another way to bring more data and more feedbacks and try to explore the physics in a way that goes beyond the traditional closure approach? And so what we've been trying to work on is to try to blend different data sets to capture and understand, again, multi-scale and multi-physics. And again, the things with, climate is that we do have some simulations, again, of different faithfulness, and we have observations, but they're usually not graded, they're pretty complicated to ingest, and so on and so forth. And again, our goal is not just to have an accurate model, is to have a model for which we can understand how the different scale interact with one another. So we've been working with, several colleagues, again, between MIT and NYU, but also kind of Open Athena, which is a nonprofit that is helping us, scale our models in a way and trying to kind of make them faster when we want to learn from very diverse set of data to try to come up with a full emulation of physical of properties in the oceans. And again, mostly we're only focusing on physics for now, that with data that comes from different sources. And so again, just to be clear, we are not looking at weeks to a few weeks in terms of prediction. We're really thinking about scale interaction on decadal time scale to understand in particular how the ocean circulation changes as everything changes. So we're still far, right, from that great goal, but I want to show you one first step that we've made, which is learning a full emulation of an ocean model at a given resolution to at least see if we can reproduce a perfect data set, so to speak, that we have, in-house. So here, again, we're back to this kind of picture of how an ocean model works, right? So we start with a field of sea surface height, velocities, temperature, salt at a given time. We usually solve it with a partial differential equation. The model has a resolution of 1/4 of a degree, and it's forced with observed wind stress and heat. And then, of course, you get the next time step. So this is a state-of-the-art ocean model run by, an operational center here in the US, NOAA GFDL lab, if you're familiar. And it's really kind of one of the best model that there is out there. So if you want to run that for yourself and you want to run for 100 years, it'll take you about 8 days and more than 4,000 CPU cores, which means you can't run it, right? So bottom line, it's usually large modeling centers that can do something like this. And so now if you want to think about, changing the forcing or changing how the parameterization inside the model are working, or if you want to do an ensemble to actually, estimate uncertainty for different, physical phenomena, the ocean that you care about, you're going to be pretty limited, right? Because you don't want to wait 8 days to run 100 years on more than 4,000 CPU cores. So they're still a long way away. So what we've been trying to think about is basically replacing that entire PDE here, not like we've done before by just adding a better closure, but literally pulling out the entire, model, if you want, and replacing it with a machine learned operator. So now what we're doing is we basically take the data from the model. We average it, and I shouldn't say subsample it. We actually filter it in space and time. And the only reason we do that is because we couldn't ingest all the data that was coming out of it. And also because we don't need all of it. So right now we filter the data on 1 degree horizontal resolution, 5 days averages, and 19 vertical levels. And everything is done conservatively, right? Because we don't want to lose heat or momentum when we do the filtering. So we still want to be conservative in a way. And we machine learn in an autoregressive way using, convex UNet. And I'm not talking about the architecture because in all honesty, I think it doesn't really matter as long as you have a big model. It does relatively well. And so it has, 135 million parameters. And then we learn the next step. Now, there's one thing that is important here is we use the previous time step in addition to the current one to learn the next two. And so that's the one thing that was extremely sensitive to is we need memory in the system. So it's not a state-to-state prediction. It's previous 2 time step to the next 2 time step. And you can think about it as learning the rate of change of temperature and momentum and giving you the rate of change of temperature and momentum. So a little bit actually kind of similar to the way the PDE would be solved. So we have basically a chunk of that simulation that is run over the last 50 years or so. We cut the first part because it's an adjustment of the model. We train on the part that is in between, and then we do some validation and testing. And the inference is done on the last 8 years of the simulation. So I'm going to show you a few things. I told you about the memory, right? That was important to use the previous 2 time step. In the loss function, we don't do much. There is no conservation added. We only learning state to state. But the one thing that we do is we do it over 4 recurring steps. So we basically accumulate trajectory over four time step, which again are 5 days averages. So you can think about trying to minimize error over 20 days, roughly, when we try to actually capture the simulation. Okay, so let's look at what everything looks like. So this is a simulation of Samudra, or means ocean Sanskrit, which is basically a full emulation, as I told you before. It looks relatively realistic. So this is depth as a function of latitude. We're looking at a temperature cross-section of the original model. So you see this kind of double bowl shaped, which is kind of the regular structure of the ocean temperature. Gets a little warmer. There's some kind of wind-driven, downwelling over here. And this is what Samudra gets. So this is our prediction. So again, captures the right structure, right? And sorry, I didn't say it, but it's a full depth emulator, right? We're not just predicting the surface. We're really kind of doing a full 3-dimensional ocean emulation. And here we're looking at wave propagation in the tropics. That is usually a signature of El Nino, so the largest mode of climate variability in the system. So this is depth versus longitude, and we're looking at temperature anomalies. So the grand truth of the model is down here. So here you can see kind of the wave propagating, both near the surface, in the subsurface, in the upper 300 meters of the ocean. And this is what Samudra is reproducing. So again, we get a very good structure of wave propagation, as a function of longitude and depth. So we get relatively good El Nino in this model. So now just let's compare, right? Because the goal was to try to do something that is faster than the original model, because you still need the original model to actually predict it. So we had 8 days, 4,671 CPU cores, and now our fastest emulator is about, an hour and a half on one A100, so one single GPU. So now you can see, right, the opportunity that this can open, where now you can actually emulate in a reduced order way your original climate model in this case, the original ocean model, a lot faster than you could before. And it's when we compare it to one of the fastest GPU-based ocean model, it's still 10 times faster, right? So there is really kind of something substantial here. And oh yeah, I didn't mention that, but of course, what's also kind of nice is that any of you can now run an ocean model if you wanted. The weights are on Hugging Face, and so is the data, so you can actually capture a lot of the a lot of the simulation and kind of play with them yourself. Okay, so now there is another big challenge that usually is kind of tricky in general, which is trying to see if the emulator is going to be stable for decades or hundreds of years, right? So now, of course, I don't have 100 years of forcing that I can use kind of easily. And so what we try to do is take a repeat forcing. So we take the forcing over 10 years of the simulation, and we keep repeating it over and over. Now, remember, it's a nonlinear model, right? So anything is possible in some ways. And now what I'm showing here is temperature as a function of time with a repeat surface forcing. And we have two types of emulator. And now one of them where we only predict what we call the thermodynamics variables, meaning the sea surface height, the temperature, and salt. And one where we predict the sea surface height, temperature, salt, but also the two components of velocities. So hopefully you can see what's going on here, right? So when we predict so first of all, it starts with the basic. All of them can be run for hundreds of years and they're stable, which is a pretty big achievement because usually there is a bit of an issue of stability, and I'll come back to it. So that's the good news. The bad news, or the semi-bad news, is the thermodynamics plus dynamics that includes all the variables. What you can see, it has a lot of kind of high frequency variability in some ways superimposed on low frequency one. Now, this could be great because technically it is more faithful to what a real ocean looks like and a real simulation looks like. The problem is that the patterns do not look really good, meaning that usually velocity has a finer scale features than the temperature and salt, except that the model, in our case, that we learn, will see high frequency patterns for temperature and salt that do not exist in the original data. So the emulator has picked up variability and it imprinted them on all the variables rather than only the one that should have the high frequency variance. So that's why we kind of, stick with the what we call the thermal emulator, because it doesn't have that bad behavior when we look at temperature and salinity, but we lose some of the high frequency aspect of it. So again, I want to give you the good and the bad in those emulation because there's still a lot to think about and how we learn about this. Okay, so where are we going with this kind of emulation, right? It was a simple first proof of concept, kind of trying to reproduce an existing model, but we've been kind of stuck with the fact that we're not research engineers. So we're doing things in a bit of a rudimentary way. So as I said, with OpenAthena, now we've been working since March, I think, in upping our data loading. So now we can go by a factor of 8. We have speeding, we speed up the training by about 25%. And so that means we can now ingest larger data sets. And so that's kind of exciting. And that's what we're working on. But the thing that I'm kind of excited about is a new collaboration that we're doing with, the same lab, JFDL, but also the Allen Institute, where we are now coupling our ocean emulator with their atmosphere emulator. So they've done, something a few months before us, where they trained an emulator of the atmospheric component of an existing model. And so now what we're doing is to actually couple those two together and build a sea ice emulator as well. So now we have a full ocean plus atmosphere plus sea ice coupled emulator. This is the error in temperature that we get, which, they're not small, but they're also not big when you compare them to an existing climate model. But actually, some of them over land, we're still trying to understand what's going on. And those over here are related to ice that we're also trying to understand. But in terms of variability, we capture the same variability as the original model that we're trying on. So it's kind of an exciting time that we actually building the capacity to do those kind of emulations at scale for the full climate system. And again, the goal is not just to have a model that does good prediction, but so we can actually understand different interactions faster. Okay. So I want to, spend a few last slides to tell you about generalization again, and because I do believe it continues to be the holy grail, right? Any method that we come up with, any, understanding, again, has to be robust under different climates. So why it's important is because we don't do it well right now, right? So I told you, climate model technically are built in a way that solve the equations of physics. For the emulators themselves, we would want them to have exactly the same properties that they can generalize to different physics. So Samudra, our ocean emulator, still has an issue that we either capture a trend or it is stable. We don't have both at the same time. So that remains a big challenge for us, which means that it's not generalizable, right? That's kind of the bottom line here. So this is temperature as a function of time in a test set. The black line is the original model, and you can see there is a warming trend, right? Because the ocean has been warming in the last few decades, and that's what the simulation is representing: a small trend in the global mean temperature of the ocean. The orange and green curves are our two ocean emulators, and what you can see is that it's flat, right? There's no trend at all. So in this case, we could roll out the model for hundreds of years with a repeating, forcing, and the model remain stable for many, many decades. We changed the way we did the training, and if you do it using a residual learning, or if you add a constraint, then you can actually capture part of the trend, but now you can't roll it stably for several decades. So we have either or right now. In all honesty, we're still trying to figure out, why we can have only either or. But our approach is to actually completely reformulate the model in terms of flux forms, so that conservation will have to be included in it, and we're hoping that might help us. But again, that remains a big challenge. As a, as a kind of other test to see if the model is doing the right thing or not the right thing, we try to impose a forcing, say a large warming with, over 100 years, just trying to mimic, what climate change would look like, right? So whether it's, in the Eocene or what it might be in the future or whatever, with a very large amount of warming. And we do different type of scenarios, which is, of course, very easy to do in the emulator. So in all instances, we add warming. The ocean is warming, but is warming basically at a rate that is 10 times to 100 times smaller than what's supposed to be warming at. So there's definitely a leakage in the emulator that we can't quite pin down. And the reason is because the warming is very small, and on top of a large amount of variability that we're learning, and we're only learning on a few days increment or a few weeks increment. So it's hard for the emulator to actually pick up those tiny, tiny signals that are going under, but are building over time. So I told you, right, that we want models that can actually learn across different climates, right? So we want them to actually work today, in the future, but also in the past. And so it's hard, right? Because it's not like we have data from the past, or we barely have data for the present. So definitely the past is harder, but I still need them to do a decent job for the past if I learn them on data and I learn from physics. So if we were trying to do emulation of different climates, usually what we've been seeing is that if we pre-train on, say, a simulation of what we call pre-industrial, where the CO2 level was 280 part per million, and test it on the Holocene, where actually you roughly have the same, CO2 forcing, but the climate is nonetheless a little bit different. So we would train on a simulation again from present day of the past, sorry. And this would be the error that we get in temperature. So again, if it's wide, that means the error is low. If it's not wide, that means you have a large error, right? And we do have a large error. But what we found is that if we pre-train on a lot of data from another era and then fine-tune on the past, for example, then the error is diminished. Now you can see the plot is actually a little bit noisy. We're not exactly sure what's going on there, but those things are very, very new, by the way. They're from the last couple of weeks. But no matter what, pre-training seems to help and fine-tuning on recent time. So there is a little hope that using only little data might help us. So here's another example, the Pliocene, where it's quite a different climate, and you have actually a different continental shelves. So now it's even the continents are a little bit different. So again, we pre-tune on a lot of data from a different climate period and fine-tune on the simulation that we're targeting, and then we reduce the error quite dramatically. And we could do the same for present day as well. We learn on a lot of pre-industrial data, and then we fine-tune on recent years. And again, we reduce the error quite drastically. So, a lot, and it's kind of a lesson that a lot of people in, machine learning tell you. A lot of data is quite helpful, even if it's not perfect data, right? So we seem to actually see a different flavor of it, but again, it's still early days. But it gives us a little hope that there is enough physics in the data itself, even if it's not exactly the regime that we want in, that we can capture something that would be useful. Okay, so let me close up here because I know it's been a long day for all of you, and I appreciate you taking the time, but just want to say a few things in closing, right? So really the grand challenge when we bring, machine learning and data-driven model is we want to build models that can surpass traditional methods. And it's not an easy task because we've done really well, but we kind of need to approach it in a way that continues to capture all the challenges that I mentioned, right? We want models that are accurate. We want model that we can run fast. And at the end of the day, we also want to learn something new, right? So improving on traditional method, and that could be hybrid, right? Or that could be full AI. I think we need it all, in all honesty. But quite often there are things that climate models can't do, right? We hear a lot about, there are tipping points in the climate system, but in all honesty, it's not like we have observations that shows us that, and the models that we have today are not quite up to the task. Or when we talk about, heat and oxygen uptake, again, there's a lot of the turbulence that is not being resolved that we can't explore. So, is there new physics that we're missing that we can learn? And how can we do that? By building better models. And so I think all the different points needs to be taken into account if we want to make real advances as we move forward. And so, but I think it's an exciting time, right? Just to be clear, I think it is such an exciting time. And we want those models to be robust, right? As I say, we want them to generalize well. There's a lot of talks, right? So how to do that? There's enough information in the data? Do you need a perfect architecture? Or do you need this hybrid physics plus ML? There's a lot of it. There's one that, we all think about a lot is, it's finding the right latent variables in some ways, right? So if we take F equal ma, right? So Newton's law, force equal mass times acceleration. This is something that actually is generalizable. It works if I'm on Earth, if I'm on Mars, if I'm on the moon. It's just right. So those principles actually work in any regime that you want. If you were integrating that equation, right, with initial conditions and forcing, it looks a little messier, right? You would write the position and it'll have, basically, things that are squared in it, and it's kind of harder maybe to capture, and they'll have too much dependence on initial conditions and so on. So maybe it's just that to find models that generalize well, we haven't found the right latent variable, which in cases is acceleration rather than position. And so there's still a lot, to think about, both on the physics aspect, on the numerics, on the AI stuff. And so I think it's pretty exciting time. So as a word of summary, I would say we kind of need a healthy blend of empiricism and skepticism to move forward, right? As physicists and applied mathematicians, we want to have things that are as rigorous as possible. And so we need to be able to question everything we do, but we also need to be able to embrace the empiricism that comes with data and AI. And so I think it's an exciting time. And happy to take any questions if there are any. Thank you very much.